Hello everybody, in this video we are going to continue our conversation about how to simplify radicals, specifically square roots. We're also going to have a conversation about like terms, because just like we can add and subtract like terms that have x's and exponents, we can actually do the same thing with square roots, but we need to know what is considered a like term so we can simplify radical expressions. So in the previous videos, we did talk about what we need to do in order to break down a square root that is not a perfect square. So definitely go back and look at some of those videos if you have any questions. But one of the main things that we're using is our perfect square list. So I went ahead and took the perfect square from the front of our page and added it to the back so we don't have to flip back and forth. So there is a place on the top up here where you can write your numbers that are considered perfect squares. Because in order for us to be able to simplify a radical, we need a perfect square to do it. So before we do anything else, let's go ahead and talk about what something would be considered a like term. So when we're adding and subtracting in an expression, we can only add and subtract numbers that have the same variable. But I also want to make sure that you understand that it's not just enough for it to have the same variable. It also has to have the same exponent if there's an exponent. So let's look at these examples right here. So right here we're looking at the 2m, and we have three options, and we have to find the one that would be considered a like term. If you had to add and subtract something to 2m, what would it be? So the first thing I want to point out, it is not going to be this first one. Because even though they both have m, this one has a square and this one doesn't. So this one is not a like term. Close, but not a like term. This one also is not a like term because they don't even have the same letter. This is an M, this is an N, not the same. So they could not be added or subtracted if they were both in the same expression. Now, if you're looking at the last one, this one is our perfect square. So the number itself in the front does not matter. The only thing that matters is that they have the same variable and it's also raised to the same exponent. So even though we can't see, they do end up having the same exponent, which is an understood one. So if you were to see these two, these are the only two that can be added and subtracted in the expression. So let's look at this x squared here, and you're going to notice that the 2 has an x squared. So the only other number here that has an x with a square is going to be this one right here. So this one's going to be our like term because it has the same variable and it has the same exponent. Even though this one has an x, notice it's raised to the third power, not the second power. Notice that this one's raised to the second, but doesn't have the same letter. This one's a p and that one's an x. So these are not like terms. So when we take a moment and look at the last one here, you're going to notice the same thing. We have an a to the third power. The only one here that has an a to the third power is this one in the middle. Not a to the second, not a to the -3. So these are our like terms. So we know that. We kind of already know that, and we've already been working with these kinds of numbers. But when it comes to square roots, it looks different, but the concept is the same. So if I'm looking at this one right here, this once again is my number in the front, my coefficient. I'm not looking at that number. I'm looking at what's behind it. So notice that this one over here had an m. Well, this one has a square root of 2. So if I'm going to combine, if I'm going to add or subtract, I'm looking for something that also has a square root of 2 attached to it. So that one's a square root of 3, so no. That one's a square root of 3, also no. And notice that they were exactly the same. But this is the only one that has a square root of 2. So notice that we have this negative floating in the front. It's just a -1. So because they have the same square root of 2, I can now say 3 minus 1, and my answer would be 2. 2 square root of 2. Because these don't change. They just come along for the ride. All right, so once again, I have this -1 in the front. I'm not worried about that one. I'm just worried about the square root of 5. So this, not a square root of 5. This, not a square root of 5. But this one is. So this one is my like term. So because they both have square roots of 5, I could say -1 plus 2. And then I would say -1 plus 2 is 1. And then add the square root of 5 to it. So if we look at the last one, this one has a square root of 7, not, and this one has a square root of 7. So this is my like term. I would say -2 minus 3 would give me a -5 square root of 7. So the number inside the square root and the square root is just a like term. It's what we use to figure out what can and cannot be combined. So let's look at a couple examples. So we're actually going to start with something we already know how to do, which is this one right here. So notice that we have this 2x and we have this -6x. So because they both have x's, we're going to combine the 2 and the -6. 2 minus 6 gives us -4. Bring down the x. So notice how that numbers change, but the variable does not. All right, same thing. We have this 4 and this 3. Since both of these don't have variables, then that lets us know that they're the same kind of number. They're like terms. So we're going to say 4 plus 3 to get 7. And since these numbers did not have a variable, your answer also doesn't have a variable. This is done because we cannot keep on combining this because one has an x and the other one doesn't. We're familiar with that. We know how to do that. So what happens when we change our letters like x to square roots? Could we still do the same thing? Could we still identify like terms and then combine them? So let's look at this example right here. So this one has a square root of 2. This one has a square root of 2. And this one has a square root of 3. So the only ones that are like terms are these ones right here. So we're going to take just these two, combine the numbers. Ignore the square root of 2 and just focus on the numbers. 2 minus 3 would be a -1 square root of 2. So just like when we put together the 2 and the -6 to get -4 and then brought down the x, we put the 2 and the -3 together to get -1 and brought down the square root of 2. That's it. And so even though this one is still part of the problem, we can't combine it. So we just bring it down, and this is our final answer. We can't combine the -1 and the 3 together because they are not like terms. Because this one has a square root of 2 and that one has a square root of 3. They're not the same. Just like when we don't combine the -4 and the 7. They're not the same. This is our final answer. So we're actually going to stop right here with this one because we can't break down the square root of 2 any further, and we cannot break down the square root of 3 any further. And you're going to see that change in this next problem. So let's move up and let's look at this one right here. So before I do anything, I'm going to see if I can find like terms. This is a square root of 18. This is a square root of 12, and this is a square root of 12. So that means that both of these are the same. I can actually put the -2 together with the +3. So I'm going to bring down the 2 square root of 18. And then I'm going to look just at the numbers in the front. -2 plus 3 gives me a +1 square root of 12. Now, even though I can't combine both of these together, because this one's the square root of 18, this one's the square root of 12, we actually have to break down this 18 and the 12. So what I'm going to do is what we did on the front page. Find the factors of 18. Now, if we've already done the number of 18 before, you can just go back and look at those numbers. Or you can just redo them like this. So the biggest perfect square is 9, so we're going to use 2 and 9 to break that down. So we're going to say 2 square root of 9 times the square root of 2. So I kind of skipped a step. Hope that doesn't throw anybody off here. And we know the square root of 9 is 3, so we're going to say 2 times 3 plus the square root of 2. And that actually gives us 6 square root of 2. Now, we still have to do the same thing with the 12. So I'm just going to use this side right here to find all the factors of 12. So 2 and 6, 3 and 4. So if you go through this one does have a perfect square. It's a 4. 6 is not a perfect square. 12 is not a perfect square. So this one is the one we're going to use. So we have a positive 1 square root of 4 times the square root of 3. We know the square root of 4 is 2. So we're going to say 1 times 2 square root of 3. If you multiply these together, you get 2 square root of 3. Now, if we get to the end and both of those are like terms, then keep on putting them together. But because this one's a square root of 2, this one's a square root of 3, we cannot combine this. So not only did we combine like terms, we simplified our expression as well. So this is our final answer. So we're going to be able to look at this one right here, and at first you notice that this is a square root of 27, a square root of 2, a square root of 12. This one cannot be simplified any further. 2 is one of those numbers that cannot be broken down any further, but 27 and 12 can. Now notice I already have the numbers for 12 right here, so I'm just going to recycle them, okay? So right here, I'm going to say minus 3 square root of 2 plus 3 square root of 4 times the square root of 3, because we're replacing the 12 with 3 times 4. All right, I'm actually going to keep on going. Okay, this becomes, the square root of 4 becomes a 2 square root of 3. 3 times 2 gives us 6, so I'm just going to keep on bringing this down. That right there becomes 6 square root of 3. So even though these cannot be combined, that's still part of our answer. Now, we intentionally left off the 27, so we need to break that one down. So I'm actually going to use a space over here to do 27. Now, you can go to the front, and if we already found the numbers for 27, we can just recycle them. So let's go ahead and write these ones down. All right, so 2 does not divide into 27, but 3 does. So 3 times 9. 4, 5, 6. Okay, I think that's it. I think these are the only numbers for 27. All right, so we can see that 9 is a perfect square. So we're going to start at the top and do 3, the square root of 9, times the square root of 3. We know the square root of 9 is 3, so 3 times the square root of 3. 3 times 3 is 9. Bring down the square root of 3. And as you can see here, we actually do have like terms. So this one has a square root of 3. This one has a square root of 3. So that means that I can actually put together the 9 and the 6. So 9 plus 6 gives us 15, square root of 3. And since this didn't get used, bring it down. So I am going to point out that order does not matter as long as you have a 15 square root of 3 and a negative 3 square root of 2. It doesn't matter if you write it this way or if you write it backwards. Put the negative 3 square root of 2 first plus 15 square root of 3. So as long as they match up in numbers and square roots and signs, then everything works. So like I said, in order for us to be able to do something like this, we need to know how to break down those square roots first, and then from there be able to combine like terms. So y'all, we just did several examples here. I hope that these examples have helped, and I'll see you guys in the next videos.